Have you ever heard of the ideal gas law? It's a fantastic rule in science. It says that for a gas, its pressure, volume, and temperature are all connected in a simple way. The formula, PV equals nRT, is one of the first things many of us learn in chemistry. It works really well for gases under what we call normal conditions, like the air in this room right now. Scientists use this law to make predictions, and most of the time, those predictions are pretty darn good. It's a cornerstone of thermodynamics, a real classic. It assumes gas particles are just tiny points zipping around with no volume and that they never attract or repel each other. But here's the thing, the world isn't always ideal. What happens when you put a gas under really high pressure, or cool it down until it's super cold? Well, those little assumptions we made start to fall apart. In reality, gas molecules do have a tiny bit of volume. They aren't just points. And when you squeeze them close together, they start to notice each other. They can attract one another, kind of like tiny magnets. When this happens, the gas doesn't behave ideally anymore. The simple, elegant, ideal gas law starts to give us the wrong answers. It's a glitch in the system. Think of it like a dance floor. When the floor is mostly empty, people can dance around freely without bumping into anyone. They can move anywhere they want, just like ideal gas particles. This is the low-pressure scenario where the ideal gas law works great. But what happens when the dance floor gets super crowded? People start bumping into each other. They can't move as freely. They might even start interacting, forming little groups. The simple rules of an empty dance floor no longer apply. This is exactly what happens with real gases at high pressures. The molecules are too close for comfort. This is a big deal for scientists and engineers. Imagine you're designing a chemical reactor that operates at hundreds of times normal atmospheric pressure. If you use the ideal gas law, your calculations for how much product you'll make could be way off. This could lead to inefficient processes, wasted materials, or even dangerous conditions. We needed a way to account for this real behavior. We needed a tool that would let us use the simple, powerful ideas of thermodynamics, but adjust them for the messy reality of how gases actually work when the pressure is on. Science needed a hero to fix this glitch. So, how do we fix our math? We use a brilliant concept called fugacity. That's a fun word, isn't it? Fugacity. It comes from a Latin word that means the tendency to flee or to escape. And that's exactly what it helps us measure. The real tendency of a gas to escape or expand from one phase to another, like from a liquid to a gas. You can think of fugacity as a kind of corrected or effective pressure. It's the pressure a real gas behaves like, even if the pressure gauge on the wall reads something different. It's what the pressure would be if the gas were behaving ideally. This idea was introduced by a very smart scientist named Gilbert N. Lewis. He realized that we didn't need to throw away all our useful thermodynamic equations, like the ones for ideal gases. Instead, we could just swap out the pressure term P with this new term, fugacity, F. By doing this, we could keep using the same simple mathematical framework, but get results that accurately described real gases. It was an elegant solution. It's like having a special pair of glasses that lets you see the ideal world, even when you're looking at the real complicated one. Fugacity adjusts our view. So how do we connect the pressure we measure with this new idea of fugacity? We use something called the fugacity coefficient. Its symbol is the Greek letter phi. The relationship is super simple. Fugacity equals the fugacity coefficient multiplied by the pressure. The formula looks like this: F equals phi times P. This little coefficient phi is the key. It's a correction factor that bridges the gap between the ideal world and the real world. For a truly ideal gas, the fugacity coefficient is exactly 1. Why? Because in an ideal world, there are no pesky intermolecular forces to correct for. Think about it this way. Imagine you're trying to push a car. The pressure you apply with your hands is the pressure. But if the car has rusty brakes that are slightly stuck, the car doesn't move as easily as it should. The effective pressure that actually makes the car move is less than what you're applying. That effective pressure is like the fugacity. The fugacity coefficient, in this case, would be less than 1, accounting for the friction from the rusty brakes. Fugacity is the term that tells us what's really happening and what the gas is truly capable of doing. Now, let's really dig into the difference between fugacity and pressure. For an ideal gas, they are exactly the same thing. If a gas behaves perfectly according to the ideal gas law, its fugacity is equal to its pressure. The fugacity coefficient phi is 1. This happens at very low pressures, where gas molecules are so far apart that they don't interact. In this situation, you can use pressure in all your thermodynamic calculations and get the right answer. It's simple, clean, and what we often learn about first in science class. The pressure gauge tells you the whole story. But for a real gas, things get more interesting. When you start to increase the pressure, the molecules get closer together. At first, the attractive forces between them dominate. Think of them as having a slight sticky quality. These attractions make the gas easier to compress than an ideal gas would be. The molecules are pulling on each other, which reduces the overall pressure they exert on the container walls. In this case, the fugacity is less than the measured pressure, and the fugacity coefficient, phi, is less than 1. The gas has less escaping tendency than its pressure would suggest. But if you keep cranking up the pressure to extremely high levels, something else happens. The molecules get so squished together that their own volume starts to matter. The repulsive forces take over. It's like trying to pack too many suitcases into a tiny car trunk. At some point, they just won't compress anymore. These repulsive forces make the gas harder to compress than an ideal gas. At this point, the fugacity becomes greater than the measured pressure, and the fugacity coefficient phi is greater than 1. The gas now has a greater escaping tendency because the molecules are actively pushing each other away. So you see, the relationship isn't static. It changes with the conditions. At low pressure, F equals P. At moderately high pressures, attractive forces often mean F is less than P. And at extremely high pressures, repulsive forces mean F is greater than P. Fugacity gives us a much more nuanced and accurate picture of a gas's state than pressure alone can. It's the true measure of the gas's chemical potential, which is the real driving force behind physical and chemical changes. It tells us what the gas wants to do. Okay, so this is some cool science theory, but where do we actually use fugacity? Well, it's incredibly important in chemical engineering and physical chemistry. One of the biggest areas is in calculating chemical equilibrium. When a chemical reaction reaches equilibrium, it means the forward reaction and the reverse reaction are happening at the same rate. To figure out the equilibrium point for reactions involving gases at high pressure, using simple pressure in your calculations will give you the wrong mix of products and reactants. Using fugacity gives you the correct real-world answer. Another critical application is in phase equilibria. This is all about predicting when a substance will change from one state to another, like a liquid boiling into a gas. For a pure liquid to be in equilibrium with its vapor, their fugacities must be equal. If you're working with a mixture of liquids, like in the distillation of crude oil, fugacity helps engineers predict how the different components will separate into vapor and liquid at different temperatures and pressures. This is fundamental to designing the massive distillation columns you see at oil refineries. Without fugacity, making gasoline would be a whole lot harder. Think about natural gas pipelines. Natural gas is transported at very high pressures to move as much fuel as possible. Engineers need to know exactly how that gas will behave to prevent problems and ensure efficient transport. They use equations of state that rely on fugacity to model the gas flow accurately. Even in geology, scientists use fugacity to understand the behavior of gases trapped deep within the Earth's crust, where pressures and temperatures are extreme. It helps them understand how minerals form and how volcanic systems behave. In the end, fugacity is a game changer because it allows us to apply the beautifully simple laws of thermodynamics to the complex, messy, and non-ideal reality of the world around us. It's a correction factor that accounts for the forces between molecules, giving us far more accurate and reliable predictions. It bridges the gap between our perfect theories and the real behavior of matter. So next time you see a high-pressure tank or a chemical plant, remember there's some cool science like fugacity working behind the scenes to make it all possible.